basic metallurgy, down and dirty metallurgy, outhouse metallurgy. I didn't go to welding school because I was good at learning from textbooks. I think, like a lot of you listening to this, I learned by doing. I learned by putting my hands on something. So in welding school, you still have some classroom time and you have to read about metallurgy, and a lot of that stuff went right over my head. It wasn't until later in life that I started leaning in, studying, buying books, reading about metallurgy, reading about welding, reading about metals. Then it started to click, started to make sense. So I made this podcast for that welding student out there who struggles to grasp the concepts of metallurgy. I made a video several years ago and it never posted to YouTube, so I'm going to use parts of that video now for this podcast. I'm going to show some short video clips while I talk about carbon steel, stainless steel, and aluminum. The basic metallurgy, down and dirty metallurgy, outhouse metallurgy. All right, let's do it. There are two things that every welder needs to know. Number one, heat affects metal. And you might say to yourself, well, thanks Pops for that big knowledge bomb right there. There's a lot more to unpack. Number two is heat affects different metals differently. Heat affects carbon steel differently from aluminum and differently from stainless steel, differently from nickel alloys. And so we're going to talk about carbon steel first. I'm going to use that as kind of a benchmark, kind of a comparison. We're not going to get into talking about crystalline structures or ping pong ball models or anything like that. This is a down and dirty video. Let's dive into some video clips to watch while I talk about this. We'll talk about carbon steel first. At the end of it, I think you'll have a really good grasp of what I'm talking about here. Let's do it. One common practice for really thick carbon steel, medium carbon steel, and even low alloys like 4130 and 4140 is to preheat before welding. It's a good practice, it's a common practice. Sometimes it's required by a welding procedure, but that's to slow the cooling rate to prevent hardening and to prevent it from getting brittle. Now, on a big thick chunk of aluminum like this, you preheat also a lot of times, but for a very different reason. Aluminum will not harden by getting hot and then cooling very quickly. In fact, it'll soften most of the time. But the reason we preheat aluminum is a very different reason. That's because it's so thermally conductive that it takes a lot of amperage to get a puddle going right away without a preheat. And also, preheat helps a lot of things like porosity on aluminum. One of the main considerations when you're welding carbon steel, especially if it's got a lot of carbon in it, like say medium or medium carbon steel and above, or even chromoly, one of the main considerations is that as it cools, if you heat it up hot enough past the transition temperature and you cool it quickly enough, it will harden. It'll get brittle. You don't want that. So it's good to think about whatever the main concern is with each metal. And with carbon steel, the main concern, one of the main concerns is getting it too hard and brittle by quick cooling. Now, chromoly tubing is a good example. This is some fairly thin wall, like 063 thin wall chromoly tubing. This doesn't require a preheat, but it's also welded with ER70 regular mild steel rod, and the reason we don't use 4130 rod on it is because it can get hard and brittle. You don't want those welds brittle. You want them flexible. You want them to be able to give. Now, here's an example of 0.120 wall thickness chromoly tube. That can be welded without a preheat also. Any thicker than that, you're going to want a preheat. Thicker metals, like this big honking chunk of 4130, definitely require a preheat, and that's usually about 500 degrees Fahrenheit. And that slows the cooling rate down. It's also good to use a kind of a welding technique that's rather slow, so that there's no quick cooling going on. And then for higher alloy metals, like a chunk of 4140, like this again, this is actually part of a stand that held an aircraft engine. It's 4140 material, very hardenable metal. And the procedure called for a preheat of 500 degrees and also to keep it 500 degrees between passes, to not let it get below 500 degrees. And so that's what I did with this infrared heat gun. A really good example of what happens to carbon steel when you heat it up and cool it too quickly is the handle of a file. The file itself is really hard. It's been hardened, but this handle is pretty soft. I can cut it with a file, no problem. But now let me just do a really super quick arc strike with a TIG torch on that same handle that I filed really easily. Now let's see what happens. I run the file over it and it's hard as a ball bearing. The file just skims right over it. That's a great example of what happens. It's also a great example of why you never want arc strikes on base metal. All right, we're going to keep talking about down and dirty metallurgy, but we're going to take a quick commercial break here. This podcast is brought to you by my online store at weldmonger.com. Got a couple of things I think will interest you if you're interested in TIG welding and MIG welding, mild steel and carbon steel, what we've been talking about so far. Number one is Jazzy Tin ceramic cup. If you're still using the old standard collet bodies that came with your TIG torch or came with your TIG welding machine, this can be a game changer for you. Relatively inexpensive to get the setup. You need a gas lens if you don't already have one, but the ceramic Jazzy Tin, the reason I like it so much is because it doesn't really require any more gas than an 8-gas lens because it's got additional diffuser screens in it, but it also just gives you a whole lot better coverage for no more gas usage. You can use a longer stick out, get that cup out of your way so you can see in tight corners. It's a great all-around cup for TIG welding carbon steel as well as stainless. The other thing is I have some free workbook downloads. Free of charge, completely free. I'll put the link in the description. TIG welding and MIG welding books and more to come. They're completely free. Take advantage of the resource. Okay, link in the description, or you can just go to weldmonger.com, hit the search bar and type in workbook. You'll find them. Let's get back to the podcast. A great example of what happens with carbon steel when you weld it is the show Forged in Fire. It's a series where they have judges and contestants that come on there, people that build blades and knives. The judges give them some criteria with the style of the blade and the dimensions, and then there's a pile of metal that they have to choose from. And in that pile of metal might be things like a lawnmower blade, a length of logging chain, an anchor, a leaf spring from a car, and they choose from that pile of metal what they think will make a good blade. And in order for a blade to be a hardenable blade, to make a good blade for a knife, an axe, or whatever, it needs to be hardenable, which means it needs to have a certain amount of carbon in it. And what happens on that show is they'll select out of that pile of metal, and then they will either just forge it from there, or sometimes they will do a little forging welding operation where they'll laminate several pieces together with flux in between, and they'll usually tack weld that to some type of a length of round stock, and a lot of times they'll use rebar for this, and then inevitably they'll put it in the forge using that long handle, and then they'll take it over to the drop hammer, and then the weld between the rebar and their piece breaks, and then it causes them time, and of course that's added drama to the show and everything. Well, there's a ton to unpack in what I just said right there. Why does that weld break so often on those shows? It seems like a recurring thing that happens all the time. But I think that, a welding instructor could show that an episode of that show, Forged in Fire, to students, but then pause it every now and then and talk a little bit about the metallurgy of carbon steel. And man, I think it would just drive the point home on what happens to carbon steel when you weld it. Okay, so oftentimes, they'll do a blade and they'll quench it in oil. They'll heat it up red hot in the forge and then quench it in oil from red hot. And the file test that they use was just like I showed a minute ago on that file handle. The file test they use is will a file cut that blade? And if it skims over it, that means it hardened. And if it bites in and cuts, it didn't harden. It's not going to make a good blade. That's a great example of what happens during the welding operation, because you know that you have to get carbon steel up to past melting temperature to even weld it. So you went way past the transition temperature, which it depends on how much carbon is in something. But let's say, just for the sake of argument, let's say it's 1600 degrees, where if it gets up past that, it will fully harden if it quenches quick enough from that. Well, melting point is 2700 or so on carbon steel, depending on the elements in it, 27, 2800. Anyway, it's around there. It's much higher than the transition temperature. So in essence, when you weld it, you are mimicking the same operation that they use when they harden a knife blade. You're heating it up and you're cooling it down quickly. Now think about that on an arc strike outside of the bevel on a test. That's why arc strikes aren't allowed in coated work, and not a good practice on any kind of work. Even a fairly low carbon steel, if it's thick enough, that metal heats up so quickly and cools so quickly on an arc strike that it can be hard and brittle right there. And so that's the reason you don't want arc strikes anywhere outside the weld. You want to weld back over all your arc strikes. And that means practicing. If you're a student, that means practicing how you nod your helmet down, practicing how you hold your stick rod or whatever you're about ready to fire off with, practicing so that you know exactly where you're going to strike. Now, auto darkening helmets have come along and have really helped a lot in this, but they don't help if you don't do it with intention. So with an auto darkening, you can see exactly where your rod is and where you're going to put it. With a passive helmet, you nod your helmet down and you hope you don't move enough, in between the time that you nod your helmet and the time you strike off. But it requires a little practice if you're using a passive helmet. If you're using an auto darkening, it just requires some intention and knowing that you don't want any arc strikes anywhere outside the weld. Let me tell you a quick story that happened to me many years ago that might save you some heartache and also might drive the point home on the effect that carbon has on hardening steel. I was working on a job on a powerhouse, and we were about ready to put a sleeve on some main steam pipe, which is, I'm going to say, was probably about 36-inch diameter pipe, maybe 48, don't remember. Heavy wall thickness, 2 to 3 inches wall thickness. And the weld was already made on the pipe, so we were putting a sleeve jacket on it that then went on some type of a pipe support. And so it was, the sleeve itself was at least an inch thick, and it had been rolled and broke to fit the outside diameter of the pipe. So we had it sucked up to the pipe using several chain come-alongs. And part of the procedure was to preheat before tacking and welding. So I fired up a rosebud and I started preheating this thing where I could get some tack welds on it. I made that first tack, but I noticed before I made even the first tack, I had a little bit of a clogged tip on the rosebud tip I was using. One of the preheat flames had going off kind of sideways. So I noticed a little soot on the joint. Well, I got a wire brush and cleaned it up real good. And then I fired up with a 7018 and made about an inch long tack and flipped my helmet up, and I heard a tick. That tack was cracked right down the middle. So I scratched my head. I don't think I had ever had a tack weld like that crack with 7018. 7018 is a pretty ductile rod. Made hundreds and thousands of tack welds just like that, no problems. So I ground it all out. Try it again. Crack. And finally, after a few tries, it dawned on me that, well, we just need to pull this thing loose, clean out everything, clean the whole area. And it dawned on me that maybe that soot was the problem. And sure enough, the carbon in the soot from that acetylene, just a little bit of carbon deposit that got up behind that joint, because I cleaned it all out that I could see outside the joint, that little bit of extra carbon made for a brittle weld metal, and it just cracked. There wasn't much strain on it because we had all the strain kind of taken up by the come-along, So we cleaned everything out, ground out all the tack welds, cleaned out all the soot, started from scratch, cleaned the tip on the rosebud. Not a problem, not a single crack in any tack weld after that. So I bring that up to say, because I've seen a lot of people use acetylene soot to smoke over threads on OLEDs and nipples on OLEDs and things like that, so that it makes for a good anti-spatter. You won't have spatter stick to threads with acetylene soot. But if you're going to do that, you want to make sure that you either mask off the weld joint itself or make sure it's far enough away from the weld joint before you use acetylene soot on threads to prevent spatter. So it was a lesson for me. I mean, that happened over 40 years ago, and I'm still talking about it today. So it made an impression on me. Carbon makes a big difference, and you also want to have that tip, whether it's a cutting tip or a rosebud heating tip. You want to have it clean. If for no other reason, it works better clean, but if for no other reason that it's going to deposit carbon and create a hardenable weld metal if you're not careful. Now, it might have been a freak accident, but again, I think I like to tell the story because it teaches a lot. And so that's the effect that carbon has on weld metal. It was mild steel, 7018 filler metal, mild steel pipe. But when I added carbon to it by the way of acetylene smoke, it made for hardenable, brittle metal. You don't want that. Okay, stainless steel is a whole other animal. It's mostly iron, but then there's plenty of chromium and nickel in there too. Have you ever heard of 18-8 stainless steel? 18/8. That means 18 chromium and 8 nickel. That's the silverware you eat with. That's stainless pots and pans, usually made out of 18-8 stainless steel, which is most commonly 304. Now, what happens to stainless steel if you heat it up red hot and then quench it in an ice bath? Not much. It doesn't really get hardened appreciably. So that makes it very different from carbon steel. So what's the main consideration for stainless steel? It's one of the main considerations is keeping it stainless, maintaining the stainless properties. And we can do that by following a procedure of limiting heat input, because when stainless gets too hot for too long, things happen in those little ping pong balls, in those little grain boundaries. Things migrate around and it loses corrosion resistance. Sometimes stainless steel is welded without filler metal. That's also called autogenous welding. And that's a good example of that is sanitary tubing like this, where it's welded without filler metal. And the main concern is a purge on the inside, an argon purge, so that the weld metal is silver and there's no crispy critters in there that can grow bacteria. Sheet metal can be welded the same way, and often is. Kitchen equipment and things like that is often welded without filler metal. The most common stainless steel is 304L, and it's welded with 308L filler. There's a whole slew of different grades of stainless steel, and it really depends on what industry you're in as far as what's the most commonly used. But next to 304L is probably 316L and 321. Now, 316L is used for its extreme corrosion resistance to chlorine and seawater, and 321 is a heat-resistant stainless steel, really used a lot in aerospace and motorsports. In order to keep stainless, in order to maintain the corrosion-resistant properties, heat input is a big consideration. I don't mean less amperage. I mean heat input can be lessened by increasing the travel speed and also using chill bars. And a 3-second rule is a really good idea for a job like this on tubing. In other words, if you can't get a puddle and get it going within 3 seconds, you probably need a little bit more amperage. You got to get going quick to outrun the heat. It's time at temperature with stainless steel. If you get it too hot and hold it there for too long, you start to lose the corrosion resistance properties. Another quick commercial break. You need a couple things to help you along your way in TIG welding stainless steel. One is the right cups. I've got TIG cup kits designed for stainless. Got all the cups you could ever need for walking the cup, as well as welding cope tube joints and things like that. But another thing is a dual flow meter. We've got Weldmonger dual flow meters now with lifetime warranty, so it's easy to get a purge on the back side of what you're welding. I'll put a link in the description. Let's get back to the podcast. I visited a pipe shop one time. I was kind of in the role as a consultant advisor. It was a favor for a friend, and the shop was having a difficult time making stainless welds that would pass destructive inspection. So they were making some stainless parts for the nuclear industry, and part of that requirement was for every 100 parts, let's say, they had to, one or two of them had to be destructively tested, which means they would do a cross-section cut, polish and etch it, look at it under really high magnification, and check for carbide precipitation. This is a 300 series stainless steel, not difficult to weld at all, but you can have carbide precipitation if you keep it too hot for too long. And that was very puzzling to the owner. He talked about, they told him to control his heat input, and he didn't understand. He said, man, you got to get it hot enough to weld, don't you? I mean, so what do they tell me? Not to get the metal too hot. What does that mean? And so I observed some of the welding that they were doing there, and it was these expansion joints, these bellows type of expansion joint, and it was fairly thin metal. Let's say for instance, it was 50 or 60 thousandths thick, but they were welding at way over 100 amps. They were just really going fast on turntables. This was they were trying to make $1 and knock out parts. And so when I watched the guy, number one, I was amazed at the skill that it required to weld that fast and that hot on something that thin, but they could do it. And the welds looked great. They were gray, but they looked great. And I watched him do it on a turntable, and man, that thing was glowing 3 inches behind the puddle, glowing red because of the heat. And so after I watched one, I said, here's what you're going to have to do. You're either going to have to slow way down and use a big flood cup or something to, limit the heat input so that you're not keeping the metal so hot for so long, or you're going to have to make some chill fixtures. And they wound up making chill fixtures because that was the key to not slowing down production. But you have to prevent the metal on stainless. You have to prevent the metal from staying too hot for too long. What happens is chromium and carbon migrate toward one another at that time that it's kept hot, and they join up to form chromium carbides, and that depletes certain areas of the grain boundaries of chromium. Well, chromium's where you get your corrosion resistance. And so if you have chromium depleted areas in stainless steel, you're going to get preferential corrosion at those areas. And that, if you think about a rock wall, look at a rock wall, and it's got all kinds of big blocks of rock and mortar joints. Okay, if you can picture that in your head, now picture there's something called mortar termites that go inside that wall and just eat that concrete and make it porous. And you can't see it's from the outside necessarily, but behind that surface, there's mortar termites. Well, that's carbide precipitation and stress corrosion. And then you get stress corrosion cracking. And if you've ever been called upon to repair stress corrosion cracking, it's just a fine spider web network of cracks. And you can't really effectively repair it with welding. It's I've got a whole story of repairing a degreaser tank like that one time, and it was just eat up. But I wound up having to silver braze a big patch on it just to make it last for another few months because they were waiting on getting the tank replaced. But I couldn't weld it because there were just hundreds of tiny cracks, and and as soon as you'd weld one, another one would pop up behind it because the metal was rotten. Stress corrosion cracking is caused by carbide precipitation. We'll go into that deeper in a future podcast, but just know that it's caused by keeping the stainless. We're talking about 300 series stainless here. It can happen to other alloys too. I've seen it happen on nickel alloys, but keeping the stainless too hot for too long. It's not just temperature, it's time at temperature. Okay? And the chill blocks make a huge difference there. It's not just welding it at lower amperage. It's heat input, its quench factor, and its travel speed all combined. But you can use one or the other to really improve your results. And in this operation, it was worth it for them to build fixtures that drew the heat out of the part. That way, they could still maintain their production, and they didn't have any problems with the metallurgists kicking out their welds as too much carbide precipitation. All right, that's a lot of words. Let's take a look at aluminum. Some aluminum alloys can be strengthened by heat treat, and some can only be strengthened by cold work. And we preheat aluminum, again, for a very different reason, mainly to just kind of assist in welding. It takes less amperage to weld it once it's preheated. It also helps a lot with porosity. Some aluminum alloys, mainly 6061 is a really common example, can be strengthened by heat treatment. But that doesn't mean it's strengthened by heating it up and quenching it. It's strengthened by holding it in an oven at an elevated temperature for several hours. Here's an example of a job that my friend Roy Crumrine did of a 6061 hydraulic tube that was welded with different filler metal than usual so that it could be heat treated, and so that the filler metal would respond to heat treatment as well as the base metal. A low preheat of 150 degrees was used just to prevent porosity and to drive off moisture a little bit. For heat treatable aluminums like 6061, it's recommended that you don't go much over 200 degrees for a preheat, otherwise you can lose strength in the heat affected zone. Now for thinner materials like 063 or something, you don't really have to worry about any kind of a preheat. But using chill bars does help in minimizing the heat affected zone and minimizing the area where strength is lost. Some loss of strength is inevitable when you weld aluminum. Now, the first thing you need to know about welding aluminum is there are some aluminums that are not made for welding. The main two that you'll hear about are 2024 and 7075. There's a few others, but those are the most common, mostly used in aviation. And like if you're looking at a big jet, most of what you're seeing is not weldable. Not welded, it's not weldable. Most of what you're seeing on that skin of that airplane is like 7075 aluminum. We don't want to weld that. You don't want to weld 2024 typically either, but it's a little bit more weldable than 7075, but you wouldn't want to make anything out of it that would hurt anybody if it broke. The problem isn't that you can't weld it without it cracking upon welding. The problem is that it may fail later on, and it may fail very unpredictably because you can't really, it's kind of like cast iron. You can make the weld okay, but then what's right next to the weld? Could be brittle metal on 7075 and 2024. The main culprit is stress corrosion cracking after welding. And so it might take a day, it might take a month, it might take a year, but it oftentimes will fail in service. So, unless you're making a tote tray or something like that doesn't really matter, I would avoid welding each one of them. Another good thing to remember is if somebody brings you something, an aluminum part to weld, and I've seen this happen. You wouldn't think that would happen in commercial aviation, but I've seen this happen where there's a part, it's got a tiny crack on it or a worn out rivet hole, and the lead mechanic says, hey, put a little weld on that thing and fix them up. And if that part does not have a single TIG weld on it, it's only got mechanical fasteners like rivets, there's a reason for that, usually, because it was not made for welding. So now if you go to weld it, you're really stepping out there. So if you see things like a ladder, for instance, probably not made out of a metal made for welding. Because if you look at the design of some ladders, it's like, man, that would have been a lot easier if they just welded it. Well, they would have weakened it. It might have cracked. They don't want the liability of a failed weld. And so, again, if there's a part that somebody brings you to weld, especially an aircraft part, if you're, because it shouldn't happen, but it does happen. People think that a TIG torch is a magic wand sometimes, and they think that it can just wave it over the part and it'll heal all the cracks, and that's just not the case. And aluminum is the biggest one. Most most stainless steels and nickel alloys and titaniums and cobalt alloys are all weldable through fusion welding processes. And even 7075 and 2024 are now weldable using friction stir welding, but not arc welding, not fusion welding. And so just a word to the wise about that. Once again, the main two things, heat affects metal. You can't get away from it, and it affects different metals differently. We saw it affects carbon steel. You heat it up and you quench it, it can get really hard and brittle. Aluminum, the way that it's heat treated is way different. There's a lot more to unpack. Stainless steel, different than those two. Stainless steel, why is it stainless to start with? Because you need it to be stainless, because it's exposed to chlorine in a pool, or because it's food service and it needs to not grow bacteria. And so you need to protect those stainless properties by limiting heat input. Hey, I hope this helps. I got a lot more for you. Stay tuned. When I was in welding school, we had book learning and we had lab learning, and all this metallurgy stuff went right over my head. I couldn't wait to get back out in the booth and just learn how to pass a welding test. But I think it limited me a little bit early on in my career, not fully understanding the differences between carbon steel, stainless steel, and aluminum, and going just a little bit deeper than what some old timer told me about the need to do this or that. That's the reason I tell these stories. That's the reason that I do these podcasts, because these are the kind of things that I would love to have heard when I was in welding school. So I hope it helps. Remember to take advantage of the free workbook downloads. Link in the description. We'll see you next time.